Okay, so let us continue the discussion on turbofan engine. So, we have looked at the performance analysis or the thermodynamical analysis of turbofan engine. So, now there are different variant of turbofan engine which are possible. So, the one which now we are going to discuss on now is the mixed flow engine. So, then from mixed flow, so this means that the mixed flow engines where which suggest, as the name suggests, that the hot and cold mixed gases, they are mixed. So, there could be of two types of that kind of engine, either it could be single spool or it could be two spool. So, previously it was used in military application, but these days it is used in also civilian aircraft and pretty much in all military aircraft. Typically one of the example is CFM 56 series, which is a two spool engine of civilian aircraft. So, it is just like the cold air which is coming out of the fan for the cold part, which is not going to be exiting out, that will be mixed somewhere. So, let us look at that. We start with the two spool mixed flow engine. So, that is we will just look at that, then the single spool would be much more easier. And if you look at the schematic, so this would be the schematic of that. Let us say we have this, and then that goes out, comes here, here the comes, and then we have this one comes here, goes like that, goes like that, and then the second set which will be there, this will go like this. So, here is the combustion chamber, then this is there. So, now we can mark the station. This is a typical layout of two spool mixed turbofan. So, let us say this is station A, this would be 2, then we come here, that is 3, come here 4, 5, 6, then 7, we have 8, 9, we get 10, and somewhere 3 prime, just to, and the TS diagram for the same. If you look at that, so we starting here at A, goes to knot 2, goes to 10, then in between knot 3 goes 4, 5, 6, 7. So, let us do it properly. So, 7, somewhere 8, and then we get 9. So, that is how the TS diagram would look like. And so, one requirement is that for the analysis mixing process are equal static pressures and also equal velocities. So, thus from the layout what we can say, two conditions are specified. One is P3 prime is P7, and then what we do, like another one is in the velocity is V3 is V7. So, which means there is no pressure loss in the bypass duct connecting the cold and hot stream, and no pressure loss in the mixing process. Then what we can write is that P naught 3 prime equals to P naught 7, which is P naught 8. Now, if losses exist in the fan bypass duct, if there are losses exist in fan bypass duct, then what we can do, P naught 10 minus delta P fan duct. So, what we can get then is P naught 3 prime. So, one more thing, so no pressure drop which is considered, no pressure drop during mixing process. So, that is another important factor, that there is no pressure drop which are considered during mixing process. So, what we can write now, energy balance for low pressure spool. So, again we are considering the mechanical efficiency of eta m1, and lambda 1 would be the conversion factor, then fan plus WLPC would be eta m1 lambda 1 WLPT. Okay. So, which straight away now we have enough expression, or so far we have looked at in details. So, we will typically put it straight, T naught 2 plus m dot A CPC T naught 3 minus T naught 10 equals to eta m1 lambda 1 m dot A 1 plus F CPH T naught 6 minus T naught 7. Similarly, if we do the energy balance for the high pressure spool, which is again we consider lambda 2 eta m2, then what we write, WHPC lambda 2 eta m2 WHPT, which straight away one can write m dot A CPA T naught 4 minus T naught 3, which would be eta m2 lambda 2 m dot A 1 plus F CPH T naught 5 minus T naught 6. So, the third, it is the mixing process which one has to consider. Now, in the mixing process what happens, the hot gases leaving the low pressure turbine and the cold gases leaving the bypass duct are mixed. So, if you look at this, this is where this is the hot gases coming, this is where the cold gases coming, and they mix at station 8. So, both the core of the engine. Now, from the first law of thermodynamics, what we can write, enthalpy at there plus 7 would be enthalpy at 8. Okay. So, 7 is in the core and this is in here. So, what we write, like beta m dot h CPC T naught 3 plus m dot h 1 plus f CPH T naught 7 equals to m dot h 1 plus beta plus f CPH T naught 8. So, this should be this is beta is, so m dot h means whatever going through the hot portion of the engine. So, that gives us back beta CPC T naught 3 plus 1 plus f CPH, then CPH T naught 7 equals to 1 plus beta plus f CPH T naught 8. Now, one can do that or basically like better evaluation of the gas properties after mixing. So, we can do the mass weighted average. So, mass weighted average. So, if you take the at station 8 the mass weighted average, what we get Cp at 8 would be 1 plus f Cp7 plus beta Cp3 divided by 1 plus f plus beta. Similarly, R8 would be 1 plus f R7 plus beta R3 divided by 1 plus f plus beta, and gamma 8 would be Cp8 minus R8. Now, considering the real gas of mixing where normally the losses are encountered and a pressure drop is associated with the mixing process, and such pressure losses are either given or as a value of delta P mixing or as a ratio in the mixing process. So, then what we can write, P naught 8 is P naught 7 minus delta P mixing, or we can write P naught 8 equals to Rm into P naught 7, where Rm is less than 1. Typical values are around 0.98, something like that. So, that is Rm is the mixing ratio of the mixing process. Now, we can check the nozzle choking condition. So, we have already mentioned so many times whether the nozzle is choked or not. If so, we have to look at the critical pressure, nozzle is unchoked, then the exit velocity at V9, this would be now 2 gamma C R T naught 8 eta n gamma C minus 1 minus P A by P naught 8 gamma C. Okay. And if nozzle is choked, then V9 is quite straightforward. This would be gamma C R T9 or 2 gamma C by gamma C plus 1 or T08, and equivalent thrust force which is given as m dot A 1 plus F plus beta V9 minus 1 plus beta U plus A9 P9 minus PA. So, that is what happens, what you get, and then also we can find out TSFC m dot F by T. So, that is how one has to look at the mixed flow engine. Now, another one could be the same engine where we can use for the with a sort of an with afterburner. So, this is another engine where you have mixed turbofan with afterburner there. So, this, I mean, military aircrafts are powered by low bypass ratio turbofan fitted with afterburner, but so that is one of the important condition for the military application, that you need certain acceleration, maneuvering and all such thing. So, if you look at this diagram, this is starting from the intake, this is a fan, then this is the fan duct, you have the core of the engine where compressor, combustor, turbine, then there is a mixing, and after mixing there is a afterburner which is sitting there before it is allowed to pass through the nozzle. So, which means, say, whenever we have looked at so far before unmixed turbofan, when we looked at previously, in unmixed turbofan you have afterburner sitting after the turbine, but now in the mixed where the hot and cold gases are mixed, then the afterburner is used to re-energize the incoming hot gases here and then pass through the nozzle. And there are multiple like this kind of things, like Pratt and Whitney has a sort of an series which, for example, let us say they have F100 220, then they have F100 229, they have 232 different series, then Eurojet has EJ200, G has F110, Rolls-Royce has MK104, Russian engine is RD133. So, there are different engine manufacturer, but one thing by this time it should be clear, there are only few engine manufacturers, because whenever we pull up this information every time when you look at these things, that this when we talk about all this, we have either Pratt and Whitney or General Electric, which are US based company, then we have Snecma, which is France, then you have Rolls Royce, which is UK company, and or the Russian engines like this. So, there are only few engine manufacturers which actually produce engine. And now, this guy is essentially, one can think about, it is a forward fan, mixed afterburning, low bypass ratio. So, low bypass ratio turbofan engine. So, this is a low bypass ratio turbofan engine. So, quickly we can look at the block diagram of this one. The block diagram will give you an idea about, like if I look at the block diagram, how to do the analysis. Maybe we are not going to carry out the detailed analysis, because this would be pretty much similar, but only thing, once you have the TS diagram and the other stuff, probably one can. So, 1 2 2, then you have 2 to 3, 3 to 4, then 4 to, you go to let us say 5, then you come to 6, then which is go to 9, then 6 comes to somewhere, this is 8, and then 9 comes to this comes to 10. So, that is the TS diagram, and one can see the TS diagram, and then so the other thing is that put the like the block diagram also. So, what will happen by looking at the TS diagram, block diagram would be quite easy. Like you have intake where you get M1, T1, you get P1. From intake you go to fan where you have P02, T02, then you have M dot AC which is cold, then you have fan pressure ratio pi F. Now, from fan it goes to sort of an P03 and T03 which goes to compressor. Then there is a compressor pressure ratio, then from compressor you goes to combustion chamber, this takes you P04 and T04 where you inject M dot F. Now, from there it comes down to sort of a turbine. So, turbine it comes P05, it has T05, and then also at the same time the fan it goes compressor, from where this also goes, that is WC, and also fan, this is WF. So, this goes in, then in between there could be, here is the mixture. So, mixture it goes T06, P06, and also some values, and you have duct. Now, duct get input from T03, it get input from P03, and then duct. So, here we will just little bit, we have P06, let us say T06, from duct also this goes, and then here it goes T07 goes P07. Okay. From mixture what comes out is goes to AB, and that comes out P08, T08, and then you inject here M dot F AB afterburner. Finally, it goes to nozzle where it enters P09 and this is T09, and you get T010, V10, and this goes here. So, that is pretty much a block diagram that you can see, and that probably. So, this also one can think this is a single spool. So, that is why single spool. Now, similarly, if you look at a two spool, then the diagram would look slightly different. It just, let us say, if a two spool mixed turbofan plus AB. So, if you look at that, so that would be like, here is the CG, then you have it, so that goes, so here is the combustion chamber, and that's connect, and maybe this one slightly we can extend, and this is where probably we have afterburner. So, this is station 1 A, then this could be 2, here is 3, 4, 5, 6, then this is 7, 8, then this is 10, afterburner it would be 11, finally it is 12. So, that is how it looks like, and similarly for this case the TS diagram would be, can be drawn similarly, like this is starting A, it goes to 2, 2 to 10, then 3, 4, 5, comes 6, then 6 to 7, somewhere 8, and then this goes somewhere 11, so 8, it comes like 9, or it comes to 12. So, this is how this diagram would like. Same conditions necessary for mixture which we have already discussed. So, for same stands for ideal condition, it would be P naught 10, which would be P naught 7, P naught 8, P naught 8. Normally mixing process is associated with pressure loss, which can be taken into consideration by delta P mixing, and then or we can write P naught 8 equals to R m into P naught 7, where R m is less than 1. So, P naught 1 is the total pressure at the outlet of the afterburner, and outlet temperature would be T naught 11, which is also probably known in advance. So, because that may be the maximum temperature which allows to have the engine because of the material consideration, and but this could be quite higher than the this engine. And quickly doing the mass balance for afterburner fuel air ratio would be m dot FB by m dot C plus m dot H. So, NRD balance would give us Cp 11 T naught 11 minus Cp 8 T naught 8, eta afterburner Q heating value Cp 11 T naught 11, or P 9 A would be P naught A minus delta P A B. And so, again the nozzle should be checked for these things, and V 12 would be 2 Cp 11 T naught 11 1 minus P A by P naught 11 gamma 11 minus 1 by gamma 11, and thrust would be m dot V12 minus m dot A V infinity, where m dot A is defined at m dot C plus m dot H plus 1 plus A plus m dot A B, which is m dot C plus 1 plus F 1 plus F A B. So, the thrust force we can rewrite m dot C plus m dot H 1 plus F 1 plus F A B V 12 minus m dot C plus m dot H into V infinity. So, also similarly for the 2 spool turbofan with afterburner can be calculated. So, we will stop the discussion here and continue this discussion for other different kind of configuration in the next lecture.